In this video, I'm going to take a look at what linear programming is in a linear mathematics class, and also feasible set solutions. Let's first take a look at what a linear programming problem is. These problems are ones where a cost or profit are being maximized or minimized. It could be other things other than cost or profit, though those are typical. And I would use this model if I knew all of my relationships, variables, were linear. And I wanted to know the best combination of these products to, say, minimize manufacturing costs. Likewise, if I knew the various factors that affected my profit were linear, I want to maximize my profit. If the relationship between the variables is something other than linear, then you can't use linear programming and you approach the problem with a different approach. So let's take a look at the next piece. Now let's say we have a situation that's been given to us and we want to know if something is or is not a solution. So this is objective 2, feasible set solutions. The feasible set is a part of a graph that provides reasonable answers to a problem. The feasible set is determined by a list of inequalities. The list of inequalities is provided or needs to be constructed based on information provided. When working with feasible sets, it is useful to shade the false sections for each inequality, and the feasible set for the entire system will then be the white section of the graph. In this particular example, I'm not going to go into the graphing. Instead, I'm going to go into how to check if an ordered pair is actually a solution to a feasible set. Now, checking to see if an ordered pair is a solution to a feasible set is actually the same as checking to see if an ordered pair is a solution to a set of inequalities. So over on the left, you can see that there is a set of inequalities. And that set of inequalities then follows with given an ordered pair. And what this is trying to say is, okay, over here on the left, I've got this set of inequalities, and I want to know if the ordered pair 14, 5 is actually a solution to this set of inequalities. So one at a time, take the 14 for x and the 5 for y, substitute it into each inequality, and see if we get a true or a false statement. Down below is my work. So I took the first inequality, and I substituted 14 and 5 in for x and y. I simplify with the order of operations to see I have 4 is less than 60. And that's true. I do the same thing with the second inequality. I put 14 in for x and 5 in for y. Follow the order of operations and see that I have a false statement. With the third inequality, I actually could stop and not do the third inequality because I had already arrived at a false statement. But for practice, I'll go ahead and do the third inequality. I substitute the 14 in for x. There's no y variable in this inequality, so you don't have to worry about where you're putting the value of 5 from the ordered pair. Just the 14 goes in, and I get a true statement. So we can see that 2 of our inequalities are true with the ordered pair 14, 5, but one of them is not. So if they're all true, then that ordered pair would have been a solution, but it's not, doesn't have the situation where all of them are true, one of them is false, and so 14, 5 is not part of the feasible region or feasible set. In the second example, it says find the feasible set for the system of inequalities and determine x and y to maximize the objective function, 3x minus y. Now, this is a very generic situation. I don't even have a context to know if this objective function at the end is talking about cost, talking about profit, talking about the number of protein items in a piece of food. We're going to take a very simple problem without the context of words and having to filter through all those words. So first, I need to find the feasible set. And to do that, I take this system of inequalities and I graph it. I'm going to walk through how I graphed that. First, I take the first inequality, which is x plus 2y is less than or equal to 6. I see that's in standard form. The x-intercept is 6 and 0. The y-intercept is 0, 3. I'm going to draw a solid line through these points. So we can see that down below I have a red dot at 3 on the y-axis and 6 on the x-axis. I drew a solid line through them, and I chose to shade above and to the right. Now the reason I shaded above and to the right of the line is that's where the solutions are not for this particular inequality. If I were to take any of the ordered pairs above and to the right, put it into the inequality of x plus 2y is less than or equal to 6, follow the order of operations, I would get a false statement. I'm going to shade the false area. That will leave the true area to be white, which will be easy to read. Now I take the second inequality, x is greater than or equal to 0. This only has the variable x, so it's a vertical line. It happens to be a vertical line right on the y-axis because that's where x is equal to 0. So I have a vertical line right there on the y-axis. And once again, I shaded where the solutions are not. Remember, this inequality says x is greater than 0. That would typically be over to the right. That's where all the true answers are. But I want to shade where the solutions are false or where they're not. Okay, so the blue is the second inequality. And on the third one, we have y is greater than or equal to 0. This is a horizontal line because there's only the variable y. It's a horizontal line right on the x-axis because that's where y is actually equal to 0. And then I shaded below that line because I'm shading where the solutions aren't. That means the feasible region is right here in white. This is our feasible region, or also known as feasible set. Everything inside this little triangle, all the ordered pairs, whole numbers, decimals, fractions, all of those are solutions to the inequalities that we started with. All three of those. I could pick any ordered pair in this white feasible set, substitute them into these inequalities, and they would be true in all three of them. Well, over here in the box, you'll see that I've listed several of the ordered pairs that are in the feasible set. Down a little lower, I have listed some ordered pairs that are not in the feasible set. They're out in either the red, the blue, or the green areas. Okay, once we have our feasible set, the next thing we want to do on part 5 here is find the vertices. So we want to find out what this is, and we happen to know from earlier work that that is the ordered pair 0, 3. And we also want to know what this vertex is, which happens to be the ordered pair 6, 0. And the other vertex of our triangle is 0, 0. Now, it doesn't really matter the order in which you write those. It doesn't matter the order in which you put them in the table down below. Now, then I tend to create a table. Nowhere in the directions of our textbook does it suggest to put this table, but I really like this table. And for this table, what I do is I write down all of my ordered pairs that represent the corners of my feasible set. Then I write the objective function. So the objective function was 3x minus y. If I scroll back up, we can see that that's what the objective function was. Okay, so I come on back down. One at a time, I take that ordered pair 0, 0, substitute it into the objective function. So 0 is going in for x, 0 is going in for y. I solve it, I get 0. Then I take 0, 3, 0 goes in for x, 3 goes in for y. I get negative 3. Last ordered pair 6, 0. 6 goes in for x, 0 goes in for y. I get an answer of 18. Now I take a look at these final answers and I ask myself, well, was I wanting to maximize or was I wanting to minimize? And I was wanting to find a maximum value. So because I was trying to find a maximum value, I want to take this answer of 18 and say that's my maximum that's going to occur with my objective function, and it occurred over here when I had the ordered pair 6, 0. So the final answer is the objective function has a maximum value of 18 at the ordered pair 6, 0.